Good evening, everyone. I've obviously just been introduced, but my name's Nick, and this evening, I'm going to talk about how we can perform reservoir characterization, seismic reservoir characterization, but of course, focusing on the rock physics elements and why that's so important to the process. So let's get into it. Yes, indeed, there I am. Possibly the last time that I wore a shirt, definitely the last time I wore a blazer or jacket. And I also must mention my colleague Kester Waters, who you may or may not be familiar with, as some of these slides are his work. So I just need to mention him right at the beginning here. So what we'll look at is basically focus on the workflow and what we're trying to achieve. And, setting the scene very simply up front in terms of what we're looking to do, what are our ambitions, and then moving through that workflow. And of course, there's going to be particular focus on the seismic conversion step, given how important that is when we actually start to say something about what the seismic responses mean. We'll see why it's very important to include the concept of facies in that inversion. And that's basically in order to preserve this knowledge of the rock physics as we go from seismic to elastic properties, and ultimately the properties that we're actually interested in, those being the petrophysical ones rather than the elastic ones. And then finish off there by having a look at how we might actually estimate those petrophysical properties once we perform that inversion step. So, of course, we want to know lots of things about the subsurface between the well control. That's kind of the point. But as I say, elastic properties aren't actually specifically on that list. We want to know something about the rock types and their distribution, both laterally and vertically. We want to know about the properties within each of those rock types or facies, so porosity, saturation, pressure, etc. But typically we invert to elastic properties. So, do the properties we're interested in affect those elastic properties? Can we understand that relationship? And essentially, as we're probably all aware, rock physics is that link. So it's the study and application of the relationships between those properties we want to actually estimate away from the well control and the elastic properties we generally get from the seismic data. So, of course, I would say this, but rock physics is the key to understanding what the seismic response is actually telling us and getting the most use out of it. So you can put these aims into two buckets. The first, of course, getting some kind of understanding of reservoir architecture and plumbing, so how things are connected up. I put refine here, but in many cases it can just be to actually define it in the first place. And then if we want to take it to the next level, if we can, we want to actually then, of course, build those accurate property models of the subsurface. So that's actually starting to say something about, or trying to say something about, the porosity and saturation, etc. So two very broad goals. Up front, these are some examples of the things that we might like to do. This is a two-way time thickness of hydrocarbon saturated sand that's been estimated from seismic data, basically by predicting that hydrocarbon saturated sand as a facies, predicting that facies from seismic, and then you can extract at different levels or different zones the two-way time thickness. So it already gives me an example of what I'd like to achieve, so I can actually understand maybe where's a good exploration target, or is my exploration target looking promising, or what is the architecture within the field? Can I refine that for infill wells, etc. This example is actually from onshore Canada, so it's a little bit exotic in that regard. And we're actually looking at tight gas sands. And in between those sands, you get these very thin coal beds. And they're very important to identify, of course, because if we're looking to simulate or fracture those gas sands, we need to know where the coal beds are. So this is an estimation of acoustic impedance from seismic data, and basically, assuming we can have an understanding of the uncertainty, of course, we can start to pick out those beds and really define or refine our plan to develop in this case. But of course, these coal beds generally speaking, subseismic. So if we do have a system that enables us to put those in there, we need to also think about the uncertainty, of course. So this is one realization that matches the seismic data, given the resolution of that data. But we also need to think about or capture all the other possible matches and have a look at the uncertainty. We'll talk more about uncertainty later on, but essentially you've got this concept of geological uncertainty, which is things like the elastic property overlap of each facies cluster. The other type of uncertainty, of course, is the data. So it's the noise levels, the bandwidth, things like that. And as I say, we'll have a look at that in a bit more detail in a minute. Another example in terms of plumbing, as it were, if we could estimate where the hydrocarbon versus brine saturated sands are, we can start to say something about how, for example, looking at facies, of course, with a long production history, lots of injectors in there, we could start to track where the waterfront is and say something about perhaps how those injectors are performing. And then update our plan as to where we might site infill wells. So again, at a very high level, you can see some very useful information coming out of the work of extracting that information from seismic data. Ultimately, if possible, we'd like to update our geomodels. So essentially push more seismically derived information into those models. So typically they're based on well data, sometimes well data alone, maybe with some kind of lateral variation imposed. But we would really like to extract information from seismic data and upscale it back into our geomodels, basically to make those, to ensure that those have as much information from different sources as possible to give us the best prediction in those property models, to make those the best that we can. So that's obviously kind of the ambitions and the aims, of course, very obvious stuff. In terms of the workflow, the process really needs to be backed by a well-based analysis, and this really can come under the heading of rock physics study, essentially. But essentially, you've got all the various steps there, starting top left, where you obviously need to know something about your data quality, going through the petrophysical interpretation, log data conditioning, etc. And this is, of course, a topic of an entire different presentation. But it's worth putting up here to say that we need to actually form these rock physics, or the understanding of the rock physics based on the well data. So understanding what different distinct units you can pick up, not facies in your typical sense, that your geologist might give you, but it's more what are the distinct elastic lithofacies that basically the seismic will be responding to. And of course, we fit various rock physics models to those in order to do perturbations. So, given we have a certain limited set of well control, we would like to see what the seismic response, elastic properties, AVO response would be for different saturations, other those encountered, different, maybe the sand was cleaner or less clean, higher or lower porosity, different geometry. So that's what we use the rock physics for, of course, in a modeling sense. We also need to consider the upscaling when we build impedance and amplitude models. So we need to make sure that we're looking at the right scale. So there's always an upscaling step. And then essentially we build this modeling framework of elastic impedances and amplitudes. And of course, can help us directly go and investigate seismic amplitudes if we've got a nice framework of AVO models. And the impedance models will guide us as to what we can hope to achieve from seismic inversion. So it will tell us about geological uncertainty because of the overlap or otherwise between different clusters that we have for our particular data set or interval of interest. And it will guide us to what attributes we might like to extract from the seismic. So what will be useful to actually get and how much uncertainty will be associated. So it's very important that we understand that up front and that we don't just go and invert the seismic data and we won't actually know what we're really getting out of it and what it tells us. So we need this solid framework, and then we need to somehow push that into the inversion step. Now, in the past, of course, that's not been so easy to do, but with the modern technologies that are becoming increasingly prevalent, we actually have a much better chance of maintaining that rock physics or using the knowledge that we've gained right through into the seismic reservoir characterization step. And hopefully we'll see some of that in a minute and how that's done, or one way of doing it at least. So again, at a very high level, given it's not the exact focus of this talk, your rock physics trends have an element of predictability, as it were, as in generally different geological processes and properties will have similar effects on rock properties, or elastic properties, I should say. But the actual details of those will change interval to interval, basin to basin, rock type to rock type. So, just to hammer home the point, really, that for a given area, we need to understand what are the different facies that are at play that the seismic is actually responding to. So starting on the left, this is a depth trend. So you've got porosity versus depth below mudline, West of Shetlands data. These are the sands, and you basically can see that we get a different behavior in different sands. So those are basically distinct facies. You have a kind of normal compaction trend, as it were, but you also have these higher porosity sands that come away from that trend, and you see those at depth. So the seismic is going to respond to those different units. We need to understand what the different responses could relate to, which is again your geological uncertainty. And when we actually frame our inversion, we need to make sure that we capture these changes between different sand, what effectively are different sand facies, chemically compacted versus mechanically compacted, for example. Moving to the right, we have a plot here of VP-VS ratio against volume of clay, and this is from a Malaysian reservoir. And basically what that is showing you is the effect of dispersed clay. So what you tend to get in that situation is these V shapes, typical V shapes. If you plot VP versus volume of clay and VS versus volume of clay, you'll see a non-linear, a peak. Basically, you can see the same things in VP porosity cross plots. And in terms of the VP-VS ratio, you see actually the lowest values are associated with fairly shaly sands. And again, it points to, in a kind of most basic sense, if we generate a map of VP-VS ratio, should we be looking at the lowest values in this case? And the rock physics tells us not, actually. But again, if we can capture this into a inversion scheme where we can include the rock physics, we'll do a better job of explaining the seismic response or matching it in the inversion or modeling it in the inversion process. And, as you go to the right, other examples. So, of course, Kimmeridge, organic rich Kimmeridge shale in the North Sea, can have very similar elastic properties to sandstones or gas sands, etc. And right on over on the right there, again, this idea of undercompaction or even more compacted. If there's uplift and erosion, say in the Barents Sea, you'll get extremely compacted, chemically compacted rocks, a lot more shallow than you expected. And again, if we don't know this up front, we can't really hope to say much about the properties we're estimating from seismic. We need to actually relate these estimates. We need to include the facies, because everything we see here is to do with facies, essentially. Different sand types, again, silty versus clean sands, and then various VP-VS ratio behavior, hot shales versus more, I guess you call them normal shales. And, those are two distinct facies, not just one shale facies. The seismic will respond or otherwise, and in fact, in this case, to contrast between those discrete units. So we need to split them out, and we need to be able to capture that in the inversion. And that's essentially, the rock physics going in. So when we get to that next step of the workflow, the next section, going to the seismic, again, of course, we need to think about our data quality. That's really important. We need to set expectations. Given the data we have, can we realistically really say that we could estimate petrophysical properties from that? Or is the amplitude, calibration, etc., AVO preservation, is it just not there? The imaging maybe not good enough. That's very important always. And part of that is the well tie. The quantitative well tie will give you a lot of information about whether or not your data is good enough to, how far you can push it, basically. But again, that's kind of another story in terms of the data conditioning and the well tie. We'll look in more detail at this in a moment, but your conventional approach would be to perform your seismic conversion to elastic properties from amplitudes, classify those into discrete units, your facies, and then apply rock physics transforms in reverse to estimate petrophysical properties per cluster. And the reason, again, just as I was saying, that we do that, we have to do this step first of the facies classification, is because fundamentally the rock physics transforms and relationships, they are a function or vary with rock type. And we know that from the work we do at the wells. We spend a lot of time generating trends for different rock units, and that's what we do as rock physicists. But we need to make sure that we include that in the inversion step and in the reservoir characterization step. There are some occasions, of course, where it's a much more simple situation, and perhaps we can be a lot more simple about it. But in a general sense, those transforms will be quite different between different rock types. So if we ignore them, then our predictions, of course, won't be up to scratch. So, the other aspect, of course, that we always have to be aware of, just as I alluded to right at the beginning, is that there's a lot of uncertainty, and it's going to come from multiple sources. The seismic, of course, is non-unique. It doesn't give us, we can't invert it for a single correct answer. We have the limitation of the seismic bandwidth. In a traditional type model-based inversion, you have uncertainty associated with that low-frequency model, that single low-frequency model. There's limitations to do with angle range, so potential for spread in VPVS, as you can see in that lower right cross plot. If you've got a much more limited range, it's very difficult to fit correctly to that versus a much wider range, wider angles. Of course, the noise versus the rock property overlap. So, the sands and the shales, etc. What are their elastic properties, and how much spread on those, and how much overlap? And there are other things, such as anisotropy coming in, etc. So uncertainty across the board, really. And we can basically put that, as I say, into two buckets: your geological uncertainty and your kind of data uncertainty. So getting to the kind of meat here, the crux, we will actually, as I say, want to make sure that we run the inversion as best we can, but including the information that we need to, because it's fundamentally the issue is that we're going to, it's a fundamental step, extracting elastic properties before we then go on to make any rock property predictions. So your typical workflow using a model-based simultaneous inversion would be something like this, where you start with your angle stacks, you invert for elastic properties, given a low frequency model that's needed for this process to get to absolute properties. And you need those absolute properties to get to the petrophysical properties. Then you do some kind of classification, maybe a Bayesian classification of those elastic impedances, and potentially use rock physics models in reverse, as I say, as a lookup table to predict, V shale porosity, etc. So, everyone's probably aware of the challenges with this process. You've got your rock physics, of course, at the wells, your understanding of what's going on in terms of the link between petrophysical properties and elastic properties, and then you've got your inversion. So it's very difficult to incorporate rock physics into that inversion step. And that's really because we have to give it one single low frequency model, which is actually very difficult to build as a kind of another point. Where do you actually generate that single model from? Normally interpolation of well log data, but of course, doesn't often make a lot of sense because for a variety of reasons, non-biased control points. We're drilling wells, we're not drilling them randomly. There's issues of stationarity if you're interpolating, up and down structure, or there's dip. And basically what we'll see is that having that low frequency model, that single one, makes it difficult to realistically extract facies. And really because there's almost two stages of rock physics or transforms going on. In the inversion itself, you give it constraints to make sure that you've got sensible elastic properties, so it must conform or to a certain single constraint, which essentially is your low frequency model. And then when you generate facies, you're using different rock physics, maybe the PDFs and the Bayesian classification. So you tend to get a disconnect. You're not using your rock physics right through the workflow. So these are kind of more illustrations of that. I guess if we start in the lower left here, you have a seismic trace in this case, and you've got a step function, which is the true AI that you want. But With a model-based simultaneous inversion, we need to start with a low frequency model, a single model. And, if you average everything, you tend to kind of do that implicitly when you interpolate log data between wells. If you've got a sand in one and a shale in the other, in between will be some kind of mix of the two. So it tends to average out the facies. What happens is where you've got strong seismic responses at the facies boundaries, you're doing an okay job of the red inversion result matching to the truth model. But where you get away from those strong reflectors, it will always want to wander back to the low frequency model. It's being pulled back. So you tend to go back to that hybrid kind of incorrect low frequency model. And indeed, an extension of the low frequency model issue is the fact that you need to give it a single constraint between the properties you're inverting for. So if it's a fatty reflectivity model in the inversion engine, you need a trend between AI and SI. And you basically need to stick a single trend through it in order to basically make it give you sensible elastic properties out of it. And as we've just spent a lot of time doing some rock physics work, and we put various trends in various shales and sands, just as we saw in those example images. But then when we get to this step, we say, actually, let's chuck all that out and stick a single trend to it because we have to, basically. So we kind of don't capture the physics of the problem. And again, without laboring the point, the low frequency model has an influence on the inversion. Of course it does. And if you change your low frequency model, you change your outputs. So this is just showing a simultaneous inversion run with a number of different models, low frequency models, a number of different results out of the inversion, converted to porosity using some transform. And then we have, n number of porosity estimates. And we can look at the mean and the standard deviation. And we can see basically that there's a big spread. And that's, in this case, just a function of the type of low frequency model that was used. Is it all the well data? Is it a select few? Is it interval velocity constrained in some way? Is it gear bodies which have been thresholded with trends in? All of those different low frequency models will give you a slightly different output. So it's quite unsatisfying to see that our porosity predictions can have a widespread just on related to how the inversion was parameterized. So it's that single low frequency model is never going to work for us. It basically causes us to lose our rock physics. It can't be built really in any sensible manner, actually. So it compromises our predictions in seismic reservoir characterization. And this is kind of what I alluded to before, where you've got kind of two steps going on. You have a separate step of facies classification after inversion. So PDFs for Bayesian classification using different trends, better trends, of course, because they're per facies PDFs. So yeah, you have a breakdown there. So what we actually want to do, of course, is to include facies in the inversion. And a lot of these points are actually more general about inversion itself, as in it's quite a nice way to bring geophysicists and geologists together. It's often a lot easier to look at layer-based properties than reflection data. But essentially, if we can bring facies into the inversion, we can actually establish rock physics trends, or we can use the trends we've established per facies and put those throughout the inversion workflow. And then effectively, if we can do that, as it says in that second bold point, that if we have trends, or if we can have facies as a concept in the inversion, and you have those rock physics trends for each facies, you basically don't need a single low frequency model anymore. Because if you're able to give it facies with trends, that's basically a series of low frequency models that go into the inversion rather than a single one. And then the final one is becomes an output of the inversion. So we, of course, have a technology to do this called GIFI. And basically, it's a process of establishing the distribution of facies and continuous impedances. So we'll look at that in a minute. But basically, what you do is you, in this very simple case, establish what rock types or facies you've got in your data. Can be your offset data, regional studies, analog data. And then basically, rather than trying to make a single low frequency model, you fit a model with errors for each facies that's encountered. So in this case, it's very simple because we're just looking at sands and shales, but it basically is based on the rock physics interpretation. So if we've got carbonates or different shale types or different sand types, we have a model for each. So that's kind of your rock physics with your uncertainties going in. You basically then start with a initial model, which is basically an average of all the trends that you've put in, given the assumptions about prior abundance. And then you do this step of optimization, essentially, where you basically have a seismic trace, and you basically then go in and say, okay, given that initial bland model with depth trends if needed, you come up with a first iteration of your, in this case, acoustic impedance to match to the seismic. And then given that initial estimate, you can go in and update the facies labeling. So after the first iteration, which is trying to match to the seismic, the impedances and the continuous sense, it then goes back and updates the model. So you basically iteratively update your facies labeling and impedances that go with it. So if you look at these lower cross plots of AI VPVS for each of those facies clusters, it essentially optimizes to start with this hybrid pariah, we call it, but it's basically covering all the options. And then it iterates around, updates the continuous impedances, then says, given that update, I relabel everything and so forth until I actually match the, get the convergence. So, as I say, that's called rock.jifi, stands for Joint Impedance and Facies Inversion. You may have seen it. But basically, yeah, it's Bayesian and probabilistic, which allows us to then actually come up with multiple realisations. So you can use the same process to come up with multiple scenarios, which is where you adjust your assumptions about the rock physics, basically. So if you're in frontier settings, you might be a bit uncertain about what the rock physics trends are. So we can actually then investigate those uncertainties. We can also describe the marginal posterior distribution of facies using the tool, which basically is coming up with these multiple realisations of facies. And that's, because, again, it's a non-unique problem where you've got overlapping elastic properties, band limited data. And so you can come up with lots of good high probability models, and you can analyze those realizations. So looking at the mean and standard deviation and different probability levels. So, having the facies in the inversion fundamentally gives us the ability to be consistent with rock physics, because the rock physics is per facies. These are some quick examples going towards the end of this PowerPoint talk. And it's just to illustrate how we can use this kind of technology. So this is an example from the central North Sea. The pink data in the map on the left is basically a 35 well rock physics study. So that's obviously a lot of detailed work in terms of these are the facies per interval. These are the trends, depth trends, and elastic property trends per facies. And what we've done here is use that information to build the prior model for the inversion. So just as before, we need to understand what the elastic properties of those facies are. And in this case, we've actually just been able to leverage work that's already been done in one of these regional studies. And then it's been applied to two fields in the analogous, basically, that have the same rock types that we have trends for. So here we can see the facies results with the wells shown as well, of course, for two of the fields. So it's basically already you can see the power there in that those seismic data sets are outside of the well controlled area. So in those surveys, we didn't use any of the well control in the rock physics, and we built the prior using those rock physics. So you can take that regional knowledge and you can push it straight into the inversion. So you get your facies estimates and you get elastic properties that are consistent with the rock physics trends. And it's that consistency which will ultimately help us when we come to estimate petrophysical properties from the impedances. If they're biased by the low frequency model or they don't have the rock physics trends, again, when we try and estimate things from them, it's not going to line up anymore. It won't line up with our assumptions about the transform between elastic properties and petrophysical properties. This is a further example, which is offshore Côte d'Ivoire. And basically, in this case, again, it's using a more regional knowledge to come up with pretty decent estimates of facies and impedances in the subsurface. So on the right, you can see the well which was subsequently drilled and the gamma ray versus the facies prediction. So, we're able to actually say something quite concrete about the architecture here, and that's based on actual rock physics. This is quite an interesting example from the Papua New Guinea, Gulf of Papua, where it's another aspect of the same problem with the traditional approach. So in this case, you've got this carbonate reef. You've got 2 wells that were available, and they were on the fringes of the reef in the lower porosity zones. So what you've got here actually are porosity estimates from seismic, the conventional simultaneous approach on the left and the GIFI approach on the right. And actually what we see here is that just as I mentioned, quite confusingly, the high porosity is in the bluer colors. So the core is the high porosity zone. What happens if you're making a low frequency model from the well data that's available? In this case, we never actually get to impedances in the center, which approach the porosity that was encountered by this blind well. So basically, the low frequency model isn't allowing those porosities, as it were, because it's not representative of the rocks that haven't been sampled here. But with GIFI, what we can do is say, okay, let's include in our prior higher porosity carbonate, and then it will fit it if it matches the seismic in that optimization process. So what happens here is, as a further example, is applying a cutoff to each of those. So let's focus on the lower image. This is basically saying what is the porosity thickness greater than 0.2 or 20% for each case. And again, because the low frequency model doesn't, it's basically giving it impedances which you'll never get to that higher porosity. You don't get any thickness at that above that porosity level. Whereas with GIFI, it can basically put in the facies again as it sees fit to match the seismic response. And this is backed up in this case by this blind well, where the porosity is much more consistent with the estimate there. And it's just another aspect here that in the conventional approach, we don't have the proper rock physics in. We have a single low frequency model. We can't actually get to characterize the reservoir correctly or make good predictions. Back on the uncertainty side of things, given what I was saying about the way we run it, given it's a Bayesian probabilistic approach, you can extract these multiple scenarios, which we have a few on the left there. And, in a broad sense, they all look quite similar. And that will be a function of, the age of the rocks, how much overlap there are between them. If they're very distinct clusters, then there'll be less uncertainty, as it were. And if, maybe you're in the Jurassic, for example, where there's a lot more overlap, there'll be a lot more uncertainty, as in it's even more non-unique. We can generate realisations, and we can then start to look at geological and data uncertainty. So we've got things like the mean and the standard deviation, and the P50 oil column thickness, etc. These things in here are ranking. So you basically have the volume, gross rock volume, net to gross, versus this is the probability of exceedance. And each of these little clusters of points are individual realisations. So you can basically adjust your rock physics trends, which is each actual grouping of points. So as you say, actually, maybe my errors are bigger or smaller, or my trends are slightly different. It will move you, there'll be a big variation in this case. And then within each of those set of rock physics and errors, you can extract multiple realisations, and it will then basically, that's each of those clusters of points. So it's going back to, again, investigating the impact of data uncertainty, seismic bandwidth, etc., noise levels, and the overlap in rock properties between each facies. This is just an example, again, just to show that. So you can come up with sections of, probability of the oil, saturated sand there. And, essentially this is what we need to do, because we need to make better predictions, but we also need to have a better handling on the uncertainty in those predictions. So the last slide coming in now is basically, what do we want to do is actually get back to elastic properties. So there's a number of ways we can do that, and they all fundamentally rely on us having a good understanding of the facies, as discussed. So this is just an example of using a rock physics model that's been calibrated at the beginning of the study, but using it in a kind of reverse manner. So as a lookup table, basically. So you've already calibrated this model as part of the well-based rock physics. And what we do now is we feed in the facies, in this case, VPVS ratio and acoustic impedance. And the model then says, given that facies, those elastic properties, these are the petaphysical properties that the model suggests. And an example on the left, where the red curve is the porosity prediction from seismic overlaid on the, the petaphysical interpretation of the log data. And it's just some extractions, and here we have complete consistency because we've used the same rock physics into the inversion throughout the inversion process that's then being used to extract the petaphysical properties. So you don't have that issue where you're kind of breaking that down, where you've kind of, moving towards a single trend through everything, which is pulling the responses to the center of the cross plot. And there's a lot of uncertainty in that regard. Just from that process, it's removing that because we've actually got the facies included in there and the rock physics trends per facies going into the inversion. So to wrap up, we basically need to include that link, as I was saying, in between geology and geophysics when we make these predictions. And essentially, of course, that's rock physics. And a lot of this hinges on the inversion itself. So that's where we need to make sure that we're doing the best job of bringing that rock physics through. So we need that prior knowledge of facies and the per facies rock physics trends. And that is essentially our rock physics work that we spend a lot of time doing. And the other aspect, of course, as I say, is we need to focus on the uncertainty. And if we have a system which allows us to include facies and the trends per facies, and it allows us to capture the uncertainty, then we should be in a pretty good place to improve our predictions of subsurface properties. So that's actually everything I had to talk about this evening. So hopefully it was enjoyable. And if you've got any questions, then please let me know.
Thank you, Nick. It was truly enjoyable, very interesting, very colorful pictures and interesting results, beautiful sections as well. So please, anyone who want to ask questions, unmute your microphone and raise your hand and have a chance to ask this question, or type something in the Q&A box.
Yeah, so of course, having wells in the seismic volume is a very important step. Just as I was saying at the beginning, the well tie is, upfront a key way of understanding the quality of the data. We need the wavelets, of course, for the inversion. But in some of those examples, it was just not possible because we're very frontier and there was no well control, essentially. So in those cases, what we were able to do using the technology I described here is basically to take the rock physics and the understanding of the different facies that may be present, to take that from analogous data. But it still leaves us the question of what is the correct wavelet for the inversion, the bandwidth and the phase, etc. And those basically have to become assumptions. In those cases, you can't really do a lot apart from assume something and test it. But, in a general sense, of course, the well tie is very important for any kind of inversion. And of course, as a way of QCing that inversion. But what I was saying about some of those examples is that we are able to use this technology to get results which are backed by rock physics, even where there is no well control and we can't do a well tie.
Okay, it's another one.
Yeah, shall I just go ahead and...
Yeah, please.
Yes, so it's a very good question. Basically, again, our focus, my focus is on kind of the part where you get to trying to estimate things from that seismic data. But of course, the quality of it, the noise, etc., is going to be crucial and key. And ICON, our focus, as I say, is in this QI work, this interpretation work, rather than the acquisition and processing, as it were. But indeed, part of the very first thing we should do up front whenever we're looking at the seismic data or any data, the log data as well, is to say, actually, can we get a good tie back to our log data as a kind of semi-hard data point? And if we see things like multiples and noise, is it going to really stop us from doing a good job? And we should find that out up front and basically either see if there's anything we can do about it. Can we optimize the amplitudes, or is it just going to be not going to work for that particular data set? So it's a really important point to make sure that the data is fit for purpose. Because indeed, if you just start off with poor data, it's not going to get you anywhere good. And it's a whole nother topic for discussion in terms of making that call and understanding what the problems might be and how we might fix them. But it is very important to do that.
Okay, thank you. And can I ask about your recent experience? Did you reject many data sets in the modern seismic nowadays?
I mean, it really depends on where we're trying to operate and what we're trying to do. Often if you're really trying to push legacy data sets or even 2D lines, it can be a challenge, of course. But these days we're getting a lot more good quality data, broadband data, but it's hard to say. It's very much scattered as to what you see, and that's why it's so important for every project to start with that fundamental. We call it data QAC. You might have seen that on the slides, but it's this idea of quality, availability, and consistency. So it's all that process of saying, can we explain what we see in terms of rock property variation, or is there something else, noise acquisition footprints, multiples, etc.? Can we actually pick those up beforehand and not then, otherwise you just process through, go through the workflow, and then you might be matching things to spurious data such as multiples. So every project needs that QAC phase for the log data and the seismic data before we do any of the rock physics or inversion work.
Yes, good point, thanks. More questions, anyone? Please don't be shy, unmute your microphone and ask something. Okay, it's another question from Adrian. As your prior model appears to be a set of fascist probabilities rather than well logs, does each well become a blind test? Or in another way, how much of the well data goes into the initial model?
Yes, that is a really good question. So the prior model is basically defined as a function of facies, let's say. So that's exactly right. With those probabilities, so you put the errors on the elastic properties per facies. They can come from well logs. Typically they do. They don't have to. They could come from theoretical models. They could come from analog data. So in a way, you kind of remove the wells, you kind of remove it by one step from the inversion. So what I mean by that is, in a simultaneous inversion, your model is coming from the well logs. So when you look at the inversion result at the wells, the low frequency is the same already. So you kind of cheating, because the match will be pretty decent because the low frequencies are the same. Whereas here we're building up a model of facies, the prior model, possibly based on, probably based on well log data, but it's kind of more global. So when you actually look at an individual well, you're referring back to your per facies trends, not to the low frequency from that particular well. So yes, they are more of a blind well control, because you're not directly using the low frequency from the wells when you look at them, if that makes sense.
Okay, thank you. And it's another one from Andy Binguigi. Thanks for a great presentation. Can you comment on the number of realisations you typically run to evaluate uncertainty? Do you...
Oh, it's gone.
Yeah, it's gone.
It's just gone into the answered one. I can see it still.
But how many realisations do you normally run?
Yeah, so again, it will depend. It will depend on the setting that we're in, and how much confidence we've got in our trends, basically. So yes, if I may, I might answer the second point before the first. But yes, in frontier exploration settings, you have more uncertainty on your rock physics models. So you can slightly adjust the trends and see how well they match the seismic. So you might have these scenarios, we call them, but it's basically different prior models going in, and that can be different facies as well. So if you think maybe that there's a slightly exotic facies present from geological description or based on modeling or whatever, you can add that in and see how that matches. So those are actually kind of realizations in a way. We call them scenarios, but they're those individual groupings. And then for each of those scenarios, we would run realizations from each scenario to look more at the uncertainty associated with the areas on the trends and the seismic noise. So in terms of the realizations, it will again depend on what amount of kind of uncertainty there is. So if we've got very tight trends and we know what the trends are, we've got very narrow zones, we might not need to run so many realizations. But typically, you know, it can be 10 or more. You know, it really depends on how big an area also has an impact, because of course we don't want to spend all the time doing it. But yes, it really comes down to how much confidence we have in our understanding of the rock physics and the facies.
Okay, thanks. And we have...
Yes, there's another one.
Yeah. Can I read it before? Because I'm not sure that audience is able to see the questions, actually.
Yes.
So, Nick, in a project with limited offset wells, how would you cope with facies not found in offset wells in terms of facies probabilities, etc.?
So what we can do in that case is, again, a very good question. What we would do is turn to our analog data. So, you know, published data, for example, but also, as I say, rock physics models. So that's something I've done quite a lot in the past is, you know, you can come up with a compaction trend, say a porosity depth trend for the region, and you can make some assumptions about what rock types there are. And then you essentially just use a theoretical model to say what are the elastic properties and build it up that way. So we could add a facies in from that. We've done it in the past where we were looking to see if there were volcanic elastics in the area. So in that case, we turned to the literature and found elastic properties for volcanic elastic, and then basically put that into the prior model to see if it would pick it up anywhere. So it does allow us that opportunity to almost generate these, you know, again, scenarios, but yeah, they are scenarios really, because it's again the same thing where you've got a different prior model with different geological properties, and it's just plugging in, you know, what happens if we had this or that facies. And, you know, then it'll either appear in the seismic data or otherwise, or, you know, what have you. You know, we look at the residuals and all the stuff you would normally do.
Okay, thank you. Comment from Adrian Smith. Thanks, Nick. Good talk. And then another question from Matthew Quinn. Great talk, Nick. Do you foresee any major advances in seismic inversion in the next few years?
Yes, well, so I guess I'm a little biased. Of course, we develop seismic inversion technology as part of what we do. And we're always making, you know, again, I'll have to come from my biased standpoint, but we're always making improvements to our technology. So things like doing the inversion in depth, of course, we can do that today, give or take, if we can actually get depth seismic, which is correctly depthed, as it were. But also, you know, ultimately, we're going to be looking at inverting on a stratigraphic grid. And that will really aid the process of getting the data back into updating the geo model with that. So yeah, I think that the advances will progress along the lines of making it more easy to update your geo models. So doing it in depth, running it on a stratigraphic grid, and even you know, a point getting into the details a bit of the inversion GIFI. It's a 3D inversion in that it's basically each time it does a facies classification, it's aware of its 6 neighbors, so above and below and left, right, as it were. And then you can basically use that to say something about the connectivity, so how easy or difficult it is to change facies. So what we can do also is attempt to enforce certain connectivity rules there. So if you have some idea of how connected the rocks would be, you can add that as a training image. But it's all part of the idea that we actually want to make something which is fit for purpose going into the geo model. So that's kind of where I see things headed, because that's ultimately what we want to do with the results.
Yes, thanks. And as far as I know, you have a workflow developed for depth inversion, so you're already performing it.
Yes, it will run in depth at the moment,
yeah.
yes.
Yeah. Okay, good. Yeah, perhaps you can, maybe not you, some of ICON can give a talk on depth inversion in the next year, maybe not so soon, but in a while. Yeah.
Yes.
That will be appreciated by the audience, I can forecast. Okay, so we have another question. This time is from Thomas Barling. Hi Nick, thanks for the talk. What do you do when you see trends from the well logs varying across the seismic survey? Are your trends 1D or can they be applied in a 3D sense?
Yes, so it's a good question again. There's a couple of elements to that. So in the most simple case, what we like to do is we have these trends which have a depth component, as in 1D, and we basically distribute the prior assumptions as a constant in each zone. But what we can actually do is if we have some more information, we can change that prior abundance in a lateral sense within the zone. So if we have a channel fairway, for example, we can say that a sand facies is much more likely within that fairway than on the edges of it. So you can add some lateral constraint in that. You remember that hybrid model, that hybrid prior we had, which was just a weighting of the initial trends. You can basically adjust that laterally using maps. The other thing that is nice to do, and it can be applicable sometimes in carbonates where you get that DC shift in your facies trend. So, it's the same facies, but as you move across the survey and perhaps with variable depth, you get the DC shift in the properties. And obviously we can't pick those up in the seismic, or the seismic won't push us towards that. You can actually vary the top of the trend. So you basically have a map which is a varying VP top of the trend, of the depth trend, and in that case it will be the same facies, but the elastic properties will have a DC shift across the area.
Okay, so yes, when you see the trends, you remove them. Okay. Another question. Tip Papworth is asking, can your techniques work as well with 2D onshore exploration without many wells?
Yes, so we have run it on 2D data. You don't get quite as so as I was saying, it's a truly 3D inversion in that each pixel is aware of its neighbors, and that gives us a certain amount of continuity in there, which we lose with 2D because we don't have that 3D element to it. But it will come down to whether that 2D data is has the imaging, of course, but also the amplitude preservation and the AVO there as well to do anything like this, any QI work. But there's nothing to stop us if we had good enough quality data and we had enough well control again to build that prior model, and whether that's well control on the line or if it's analog data, it's about actually understanding what are the facies and what are the elastic properties. But there's nothing fundamental which will stop us running in that situation. And indeed we have, with some success, run on 2D lines in more, in very frontier settings.
Yeah, so the key is data quality. And I remember in the beginning you showed the onshore example from Canada. As far as I know, team works in Armenian data.
Okay.
Just curious if you had any experience whatsoever on 2D on land data.
Yeah, I mean, the 2D data I've looked at has been marine or offshore, but I don't know off the top of my head if we've done any work on 2D land data. But I might be wrong there. We've got a fairly large global team, so we could have done somewhere.
All right. Yeah. Thank you. Another question from anonymous attendee. Can he comment on Ji-Fi runtimes and whether he thinks it might be possible to train a deep neural network on a number of synthetic forward models for a more performant facies inversion?
Yes, it's a good question. And indeed, we also provide tools to do just that with these deep neural networks. So, it's obviously going to be a little bit compute intensive, this kind of thing. We can do it in a couple of different ways, actually. There's this optimization approach, the so-called EM, and that basically is less compute intensive, but it searches for kind of a local optimum. So basically says, here's your starting model, and it actually very efficiently comes up with a high probability result, which is reasonably close to that model. So it's a kind of local approach. And then you've got this other version called IQP, which is a global approach, which is giving you a full description of the marginal posterior. And of course, that has a much bigger compute associated with it. The real thing for me anyway is, well, what we're doing with things like Ji-Fi is we're retaining the physics of the problem. So we're actually understanding or capturing what the facies and their elastic properties are like, and we're explaining the seismic response as part of the inversion using both the mixed discrete continuous nature of the problem, which is what the seismic is responding to those interfaces, the facies, so we should have them in the inversion, and the physics is captured in the rock physics trends per facies. The neural net stuff, the machine learning stuff is great, but we need to be sure that it's still honoring the physics of the situation, so that when we get that facies model out, is it meaningful, and can we actually use the elastic properties associated to get robust predictions of the things we need to know, the petrophysical properties. So that's why we favor this kind of physics-driven approach, is because it's actually explaining the problem better. But suffice to say, we do have tools for doing neural networks kind of work, and actually where we tend to use them is we put them on after the inversion. So you invert to facies and elastic properties, you use the neural nets to predict your porosity, etc. If that technique works in whatever situation you find yourself in.
Thank you very much. And another question I can see, Jeff Marsden asking, Nick, you've said uncertainty in the LFM limits your results. What extra information do you require to improve the LFM?
So yeah, if we're talking about a single low frequency model for like your classical simultaneous inversion, if we're using the traditional approach, which is of course interpolating the log data, what we might of course do very simply is exclude deviated wells, of course, because they may have anisotropy effects in the elastic properties that are measured. We might like to bring in seismic velocity information and include that. It would help us with that single low frequency model generation. Or we might turn to something such as if you could do a relative inversion, maybe looking at an extended elastic impedance for lithology, maybe for fluid, you could take those, you could do some thresholding, make some geobodies, put some trends in, and that might give you a less biased low frequency model. But it doesn't get us away from the fact that that model is going to be hard to build, and it's, if you do it the simplest ways to make it easy on yourself, it's not going to be correct, and we have all those problems we discussed. So then what we're really doing is we're walking away from that entirely and saying, actually, we want a low frequency model for each facies that we think is there, and then let the inversion put those facies where it thinks they should go. And ultimately, then your final low frequency model is an output of the inversion.
Yeah. Okay. Thank you. Ian Jack wants to expand on the previous question on machine learning. So expanding on the current answer, can you look ahead, say 10 years, and say how much impact artificial intelligence and machine learning will have?
It's not the easiest question to answer. I don't know if we're going to see Skynet and Terminator 3 coming down, but yes, like I say, it's for me, as long as we can use it in a manner which retains the physical aspect of it but makes our lives easier, I'm all for that. So maybe helping us identify where bad data is something that's flagged up before. Maybe helping us identify what rock physics models we should use, that kind of thing, perhaps. But of course, 10 years is a long time, and it's very hard to see. It's one of those things I find the AI ML situation. It's been around. I remember when it first came out as a big thing in the industry, an EAG a few years back, and it was all over everyone's marketing material. And I don't think we've really seen the biggest benefits from it yet. I think there's more to come, and I think it's about actually understanding where it fits into the workflow and where it brings the most value, because the danger is for me that we might try and skip the important steps, and actually it can be more harmful than good, because actually the properties, the predictions we get out of it possibly aren't as good as they could be. So I don't know if that answers it. It's not the easiest one to answer.
Yeah, thanks for the forecast anyway. Another question from Andy Binguigi. Nick, on the topic of probabilities obtained through the inversion process, do you think these likelihood are more an expression of accuracy or precision of the prediction?
Yes, it's a hard question to answer, especially this time of evening. But I think off the top of my head, I think it's looking at the accuracy, really, isn't it? A combination of both. Let's think about this. You're basically, you don't know the answer, of course, so you've got many different options which equally explain the data that you've got. So we're kind of really thinking about the accuracy of each prediction, I guess. But that's a total answer without having thought about it. I reserve the right to change my opinion in about 5 minutes' time.
Okay, thanks for the question, and Nick, probably you can note it down and prepare the question for the next presentation when you are in a relaxed mode. Yeah, thank you. Jan Jack says good answer. He had a question about the machine learning and 10 years prediction from now. Thank you, Jan, for asking. And we have one more question from another anonymous attendee. Hi, Nick. Great talk. Coming from seismic processing background, your talk helps me with understanding further down the line. What's your thought on using inversion to guide seismic processing? Thanks.
Well, it's something I think has got a lot of potential. You know, how that works, it's not so easy because you want to make it very iterative, which has challenges, of course, logistical challenges. But I think it's a very general statement. It can help us, you know, in the processing, in things like the well tie as well. If we can do very quick inversions of, you know, near to well locations, etc., and basically say, okay, are we actually managing to match, or how good are we matching the well response as we adjust our processing steps? And using something like GIFI would help you a lot in that, again, because you have less bias from that well control. But I think there's a lot of potential for it. But logistically, there are some challenges just because we really need that iterative process. If, you know, comparing, updating the inputs to the inversion, and then assessing and understanding if we're actually improving the match or not.
Okay, but the integration is possible in the future 10 years.
Yeah, 10 years. Why not?
Yeah.
Why not 10 years?
Okay, sounds encouraging. Thank you for that. And I think we covered all the questions, which I can see both in the Q&A box and in the chat box. And we spent a good hour on the talk and Q&A session. So I think it was a quite interesting, quite successful conversation. A very active audience today. And altogether we had 41 attendees at maximum, plus 5 of us who were arranging and attending the panel. So with that, I want to thank you on behalf of the AAGE and on behalf of our London community. Thanks so much for agreeing to give us a talk and for entertaining us tonight. Thanks.
Yeah, thanks everyone. Thanks everyone for coming.
And thank you audience for coming. And I just want to remind you, if you want to help us to run our local chapter and bring some more new exciting initiatives, please contact us and join our group. Okay, thank you everyone, and goodbye for now. Cheers.